All right, guys, so we're finishing the note sheet from yesterday. We have 3 questions left. It's just applying transformations, the only thing we have left to do. So I split them up. Now, writing transformations of quadratics, we do have the vertex. The vertex is the highest or lowest point of the function. We'll get more into this, especially with 2, 2, 2, 3, 2, 4, vertex form. Now, you don't have to write all this out. If you want to, you can. You don't have to. Because when we look at this here, the A value indicates a reflection in the x-axis and or vertical stretch or shrink. The H indicates a translation horizontally left to right. K is our vertical translation up or down. And we've seen all this up to this point. And we've had notation with our transformations. F of x plus k, where k is on the outside, moves it up or down. Our F parentheses x minus h, close parentheses, is our left right. And we've done these before, and really that's what we're going to be doing when we apply these transformations here. So if we let the graph of G be a vertical stretch by a factor of 2, and a reflection in the x-axis followed by a translation 3 units down, we have 3 different transformations. So I'm going to call the first m of x. Our vertical stretch by a factor of 2, vertical stretch and shrink, is our a times f of x, where a is the amount that we're stretching or shrinking the function by. And for us, our value of a is what? 2. So we'd have 2 times f of x. Well, f of x, as it's solved by us here, is the equation x squared. So we can replace f of x with its equation, which is just x squared. And if we multiply these two here, we get 2x squared. Questions on this so far? Of how we applied the vertical stretch of 2. So vertical stretch by a factor of 2. Done. Next one's a reflection in the x-axis. For our reflection in the x-axis, it was negative f of x when we applied it to f of x. But since we're not applying it to f of x, we're applying it to m of x. It's just going to be negative m of x. We're distributing a negative through the function. So, h of x. Well, what is our m of x? It is 2x squared. Now we can apply that negative to it, which tells us that it is negative. We multiply it through, well, there's only one term, so it just makes it negative 2x squared. And our last one, when we translate something up or down, it was that f of x plus k. Not applying it to f of x, we're applying it to h of x. So g of x would be h of x plus k. We'll make this nice and simple. Our k is 3, but it would be negative because it's going down. And h of x is what? Negative 2x squared. So g of x is negative 2x squared minus and that's it. I think these became a little bit easier once we've seen them and seen how they worked a few times, yes? Questions on this here? Now the textbook did this a little bit differently. Now, they gave us the formula just a minute ago. F of x is equal to a x minus h squared plus k, where a is our reflection of the x-axis and vertical structure strength. So here, they'd say a is negative 2. We get the negative from the reflection, 2 from the vertical structure strength. There is no left-right movement, so there is no h. And k is our negative 3, because it's moving it down 3. So by the book, we can say g of x is equal to negative 2 times x, well, minus 0 squared, minus 3. And gave us our answer. And yes, this works well. It does give us the answer if we apply the vertical structure strength first, reflection second, and up, down last. If we apply it in that order. If we switch the order up, this does not work. This only works if we do it in this particular order, in this particular way. That's why I don't normally show it this way. Because the way we did it, no matter the order of the transformation, it always works. It always gives you the correct answer. Did y'all see the difference there? Because if we switched the reflection across the x-axis and translation at 3 units down, it would actually be plus 3, not minus 3. Because when we apply that reflection across the x-axis, we apply it to every term. So the minus 3 would have been there before the application of the negative, which is going to cause the sign change. So it does change the values of the numbers in the order in which we apply them. Does that make sense? Same thing's true with horizontal stretch and shrink and left to right. If we move it left and then stretch or shrink it, it's going to be different than if we shrunk it, then moved it left or right. So most of the time it's nice. Some of the times it's not. Luckily for us here, we only have 2 transformations. Vertical shrink by a factor of 1/2, followed by translation 2 units up. We can start with the vertical shrink by a factor of 1/2. So it's our a times the starting function, a times f of x. Well, a in our case is 1/2. Well, our function is still just x squared. So we have 1/2 times x squared. Well, what is 1/2 times x squared? Which is 1/2 x squared. Up 2, so the value of k is positive 2. H of x, well, that is what? 1/2 x squared, yes? And this one here, just like the last one, we could have plugged a as 1/2, k is positive 2, and gotten there. Because as I said before, order of this matters. Let's apply it in the reverse order. So if I said h of x is equal to f of x plus k, well, that'd be our x squared plus 2. Okay. No big deal. That's an easy one to apply to it. Now if we apply the vertical shrink by a factor of 1/2, so g of x is equal to our a h of x, which would be 1/2 of h of x. Well, our h of x is x squared plus 2. We distribute through. 1/2 times x squared is indeed 1/2 x squared. That matches up correctly, yes? But I also have to multiply that 1/2 with the 2, which makes it plus 1, not plus 2. So we kind of see the distinction. Because with vertical stretch or shrink up down, we need to apply the stretch shrink, then the up down. Because if we do it in the reverse order, it does affect the other. Same with left, right, horizontal stretch shrink. Anything that's affecting the output, the y, that gets applied to the whole function. The order of those matters. So we're applying that in our horizontal left, right. They don't have as big of an impact on each other. Questions on this here? Well, let's do one last one. Let's do this one here. Let the graph of g be a horizontal shrink by a factor of 1/3 and a reflection in the y-axis followed by translation 2 units up of the graph f of x equals x squared. So first thing we'll have is horizontal shrink. I'll call it h of x. Our horizontal stretch or shrink is going to be our f of ax, where a is our factor that we're stretching or shrinking the function horizontally by. Now, horizontal stretch or shrink, we got to be careful because they said it was a horizontal shrink of 1/3. We're not plugging 1/3 into the function. We have to flip it to 3/1 or just 3, giving us f of 3x. Now, our original was f of x equals x squared, yes? I'm going to replace the x in f of x with 3x, giving us 3x squared. We're going to leave it. We could square that term, but we'll leave it. Especially if it was like 3x plus 1 squared, we'll leave it alone, because the only way to simplify that is to multiply 3x plus 1 by 3x plus 1. Here it's a little bit nicer because it is a single term, 3x times 3x. We could do that. We'll do it here in a minute. But we get this here. Horizontal straight by a factor of 1/3 done. Our next one is a reflection in the y-axis. So it's normally f of negative x. But here we'll take, since we're applying it to h of negative x. We're going to apply every x and h of x with negative x. So we have parentheses 3 negative x squared. Questions on this here? What's 3 times negative x? It's just negative 3x. Reflection of the y-axis, done. Now all we have to do is translate it 2 units up. Well, our m of x is our negative 3x squared. Our value of k is plus 2, yes? Incidentally enough, that is the answer. Now, if we wanted to, we could simplify it a little bit. Negative 3x squared. When we square something, we're multiplying it by itself, yes? If there's a single term, we square both. We say we multiply both terms by itself. Here we're saying we have negative 3x times negative 3x. Negative 3 times negative 3 is 9. X times x is So our negative 3x squared is 9x squared plus 2. Now, we did have a problem similar to this in chapter 1. I think it was, I remember the absolute value of negative 6x, I think there was plus 2. But the absolute value of negative 6 was part of your answer. This is also the correct answer. And there's a reason for this. If it was negative 6x plus 2, we would leave the negative there. But since it's just negative 6x, there's a reason for this. Part of the properties of, let me move this down just a little bit. One thing we can say, and I'll see if y'all are okay with this. I'm not going to worry too much about the plus 2, it's not important. But the absolute value of negative 6x, would we agree that it's the same as the absolute value of negative 1 times 6x? Those are the same thing. Now it seems like I'm cutting hairs with this. One of the properties of absolute values is that the absolute value of m times n is the same as the absolute value of m times the absolute value of n. We can split it. So here, that means I can take the absolute value of negative 1 times the absolute value of 6. What's the absolute value of negative 1? 1. So it just gives us the absolute value of 6x. Because that negative is going to come to naught in the end. That's why those are the same. Now if we had 6x plus 1, we could do this. But that means this would be 6x minus 1. We'd have to factor out and do more things with it. So if we had another number added or subtracted there, we just leave it. There's no point. Does that make sense? It's also part of the reason why if we have just negative x squared, it's just x squared. Doesn't have a big impact on it. Questions on this here? Those problems should look familiar. I think that is the exact, well, it is the exact same assignment from yesterday. So this doesn't add anything. I wanted to go over that one more time so we saw the transformations and how they work.